Thank you for the invitation to speak here and for the introduction. It's wonderful to be back in Greece. Little known fact, perhaps, that my maternal grandfather actually came from Thessaloniki back around the early 1900s with his brother. So I probably still have relatives I've never met who live in this area. So for me, it's very exciting to be here with you. I have to bring my talk up, but that would be a good thing to do too while we're doing that. Always helps to have your slides. All right, so now I think we're ready. So my talk today, just to encapsulate it before I start, it has several key points. One is that indoor air quality has many serious effects on our health and well-being that I think are still underappreciated by many. That's why I've been giving this talk for a number of years. The second thing is that the importance of indoor air quality really is not reflected in the approach we take to controlling it if you look at how our minimum standards are written. So I'll say something about that. The third thing is that because we typically use ventilation to control exposures to contaminants indoors, and the air that we bring in for ventilation has to be heated and cooled, it has a significant energy penalty associated with it. And so that's how we come up with this title about integrating IAQ and energy efficiency, that we need to come up with ways to do a better job of maintaining indoor air quality while not harming our goal of having low energy use buildings. So with that, let's jump in. Buildings are the largest single energy end use in most countries, developed and undeveloped. This figure shows the United States, where we have about 20% residential end use and commercial about 18.5%, so 38.9% overall, compared to smaller amounts for industry and for transportation. So in the big picture of saving energy, buildings are very important. And then when we look at how energy is used in buildings, most of it goes for what we call indoor environmental quality control. So heating, lighting, cooling, and ventilation are four of the biggest, and three of those are related to HVAC. So the total is 59%, and HVAC is responsible for nearly half of the energy consumption of buildings. So if energy use is important, buildings are important, and HVAC is the most important single area within buildings. And I think that's something that has been widely recognized for a long time. The impact of buildings on energy use, and also using fossil fuel to produce the energy that goes into buildings, and its effect on the environment are recognized. And so when that happens, when scientists and public and policymakers recognize that, things happen. So we've had 40 years or more of major efforts to do something about energy and environment. Energy standards that started in the 1970s, the Montreal Protocol for ozone depletion, the Kyoto Protocol, which then brought climate change to the fore, and also produced the realization that what we had done to solve the ozone problem left residual problems related to climate change. And we've seen a lot of effort worldwide to switch from non-renewable, atmospheric, polluting energy sources to those that are more sustainable, PV and wind in particular. And if we think of what's happened in industry with equipment, we've seen great improvements in efficiency for just about any component you can think of. The figure on the right shows ASHRAE standard 90, now 90.1, which started in 1975, and it charts the relative stringency of it up to the current 2016 standard, and you see the allowable energy use dropping and dropping and dropping to where it's now less than half of what it was in 1975. I know there are those who think we are not reducing energy use rapidly enough, but this certainly suggests that we have made progress, at least in our standards, towards doing that. The thing that we need to remember when we're saving energy in buildings is why we use it in the first place, to go back to my original point. The World Health Organization has made this statement that I like very much about access to air and water of acceptable quality being a fundamental human right. I think that should apply indoors as well as outdoors. And the second statement here is by Björn Olsen and colleagues who are working on the revision of the European Indoor Environmental Quality Standard, that an energy declaration without a declaration related to the indoor environment makes no sense. And that ties what I was saying together very nicely, that if half of the energy use in buildings is for indoor environmental control, then if we don't have some sense of what our target is that's appropriate for indoor environment, then we're simply shooting in the dark. So what is our current definition of indoor air quality? It's based on human perception as being an adequate way of describing IAQ. So we have here the definition from ASHRAE standard 62.1, which is very much like what we find in European standards and others. Acceptable indoor air is air with no known contaminants at harmful concentrations as determined by cognizant authorities, and with which a substantial majority of the people exposed do not express dissatisfaction. We typically take 80% not expressing dissatisfaction as being acceptable. The first part of this statement, that we find no contaminants at harmful concentrations in buildings, is somewhat undercut by the fact that we rarely, if ever, measure anything in a building once we've built it. We assume that the materials we're putting into the building will result in acceptable air quality, and we leave it at that. Every once in a while we have a surprise. The other part, we have a relatively low standard, and we're assuming that a person is a good sensor for things in the air that might affect their health or productivity or well-being. How much radon do you think is in this room right now? I could have opened a big canister of radon in the back of the room, and everyone would be breathing a very high concentration of a gas that would significantly raise your chance of getting lung cancer in the future, but it's odorless and colorless. And you can think of many other things that could be in the air that have similar effects. So it seems to be, on the face of it, a rather low bar to get over. So how did we get this? By human subject tests, a lot of which were done in Europe, many of them at DTU by Ole Fanger and later colleagues there. We currently control IAQ by trying to get rid of sources that we know are bad. We've gotten radon control in buildings to reduce the source. We've removed asbestos from buildings, and generally we don't allow indoor smoking anymore. And those are our biggest successes in an IAQ. We've relatively recently, focused on moisture management in buildings to control mode, so that's a good thing. And beyond that, we mainly ventilate to achieve this 80% not dissatisfied criterion. In ASHRAE standard 62.1, that's about 5 to 10 liters per second per person. And on top of that, we had a little bit of particulate filtration. ASHRAE standard 62.1 uses the ASHRAE 52.2 standard to specify filters, and currently the requirement is a MERV 8 filter, which is 70 to 85% efficient for particles greater than 3 microns and not even rated for PM 2.5. So it doesn't really do very much with respect to health effects particles. The figure on the right here shows how we come up with the ventilation rates that we use for subjective satisfaction. You simply put a person in the chamber and ventilate at different rates and let them expose themselves to their own bioeffluent at different concentrations. And then you pull a large amount, and we find that about 7 liters per second per person on average will result in about 20% dissatisfied. And that's how we do it right now. So let's move beyond that to what the true value and costs of indoor air quality are, and I'll introduce here the 1/10,100,000 rule, which is a very rough order of magnitude way of saying that if we spend about a dollar or a euro on design, that will result in something like 10 euros of construction cost, and in the life cycle, 100 euros of operating cost. But if we look at the life of the building and what we pay for people to work in a building and what we pay for their health care and all these other costs, that's more like 1,000. So we typically have 1 to 2 orders of magnitude higher cost for occupants than we do for operating costs of the building. This was realized a long time ago. I first heard about this at a conference almost 20 years ago now in Finland. Some of the people who worked on that were Bill Fisk from the Lawrence Berkeley National Lab in the US, and also Ole Seppänen from Finland. So this table shows some of Fisk's work to estimate what we're leaving on the table in terms of indoor environmental quality by not making buildings better. And he looked at respiratory illness and asthma and sick building syndrome, and also the effects of lighting and thermal comfort, and came up with a number that was estimated to be between, in current terms, between about 50 billion US dollars and 285 billion US dollars per year. These are affordable improvements to IEQ that have consequences in terms of people's health and productivity. The total energy bill in the US is about $400 billion for buildings per year. So that's a pretty high cost there that we're bearing because we don't want to make buildings a little bit better. There are other ways of looking at this as well. Asthma is an important worldwide health problem. About 8% of the US population is diagnosed with asthma, and it leads to tens of millions of asthma attacks per year, resulting in tens of millions of lost work days and school days. And sometimes when someone's home from school, a parent has to stay home with them. So there are domino effect consequences here. Moving towards 500,000 hospital stays in the US per year, and almost 4,000 deaths. And the triggers for asthma, not necessarily the cause, but a lot of the triggers are indoor pollutants that we could do a better job of controlling that are listed on the right-hand side here. We also have in the developing world particularly a problem with PM 2.5 exposure. It may be the most significant air contaminant anywhere in the world right now, but it's particularly bad in developing countries where there's still a lot of poorly controlled biomass combustion indoors for heating and cooking. The World Health Organization estimates from PM 2.5 exposure indoors and outdoors something like 7 million excess deaths per year. Indoors, household air pollution, about 4.3 million excess deaths per year. About 56 million people per year die on average at the current world population. So this is about 1 in 8 overall, and about 1 in 16 associated with indoor exposures. And you can see some of the health effects from PM 2.5 that are shown on the right-hand side of this slide, respiratory as well as systemic diseases. So there's a big cost that results from poor indoor air quality where it exists. So the next question we might ask is, how well are our current approaches to maintaining IEQ protecting us from those consequences? So we'll go through a series of slides here looking at what happens when you ventilate buildings at different rates. And focusing on ventilation because that's what the research community tends to have done. But if we are thinking about something other than ventilation as a way of controlling exposure, just think of ventilation as a way of reducing exposure rather than a specific method. And so here we have sick building syndrome symptoms as affected by ventilation rate, and this is the average of a lot of studies, a meta-study if you will. And relative incidence of sick building syndrome reporting is called 1 at a ventilation rate of 10 liters per second per person. And what you see there is that if you double or even triple that ventilation rate, you see a significant reduction in the incidence of SBS. Why are sick building syndrome symptoms important? They're associated with absenteeism and also with people not working as productively as they might. So this isn't a very good start. The next thing we move on to is productivity measured in different ways. A lot of productivity studies have looked at what we might call task performance, which is not high-level cognitive thinking, but how fast or how accurately can someone do simple tasks like answering calls in a call center. And so here is again, a summary of many studies that sought to show what the average was. And what we see is that, again, if we started a ventilation rate, in this case of 6.5 liters per second per person, and call that our baseline, if we double or triple the ventilation rate, we might get to, on average, something like a 3 or 4% improvement in task performance, which is a quite significant improvement in productivity if you're doing it with the same workforce. So another 4% on top of what you were producing without any additional payroll cost is a big change. So that doesn't look so good either for the way we're doing IAQ in many buildings. And I should say we're looking here mainly at the kinds of ventilation rates that we see in US standards, but the same that we said about Europe with a few qualifiers. We've also looked at work done in school by school children, and here the research that I'm showing is by Bargashki and Lyon from DTU. This is an ASHRAE research final report that every ASHRAE member can download free from the ASHRAE website, which is where I got it. And the two figures here show a trend of both improved speed of doing work and a somewhat less clear trend of higher accuracy for school children when the ventilation rate per person is higher. So those are all indicative of our ventilation rates not necessarily being optimal. We can also look at infectious diseases, and there have been a number of studies on this. This goes way back, actually, because the main model we used to look at infectious disease transmissions affected by ventilation was developed by Wells and Riley in the first half of the 20th century. The data shown here is from an actual experimental study done at Tianjin University in China, where the researchers looked at 6 dormitories on the campus, and they estimated the winter ventilation rate, and they polled the occupants to determine how many common colds, rhinovirus type infections they had in a 12-month period. And it was called a hit if they had 6 or more, which is a pretty robust number to use as your target. And what we see here is that as the ventilation rate goes from 5.2 liters per second down to 1.3, we have incidence of colds in these dorms going from about 5% up to, in the last case, 35%. The other thing you might notice here is that none of these dormitories had ventilation rates in the winter that were as high as what we say the minimum ventilation rate should be, even by a perceived air quality standard, which is a problem in naturally ventilated buildings where opening windows is the only way to do it. If it's cold in the winter, we close them, and that's that. More recently, we've seen work on cognitive function, and the work that has gotten the attention is some studies that looked at the nature of CO2 as an air contaminant. It kind of mixes two things together. Does indoor air quality affect cognitive function, and is CO2 an air pollutant? And we need to kind of separate those two things. I would say the answer to the first question is quite clear, and the answer to the second one is still very much in dispute. But this study by Satish et al., a group on the west coast of the US and Lawrence Berkeley National Lab, looked at evaluation of human subjects doing a proprietary cognitive function battery on a computer while exposed to different levels of carbon dioxide that were created by injecting pure CO2 in a test chamber. So the important thing here was the bioeffluent concentration didn't change, only the CO2 concentration. And they found that even at 1,000 parts per million, which is generally considered to be an acceptable indoor concentration, it appeared that there was a deficit in cognitive function that was statistically significant. Of course, at 2,500, which was the other level they looked at, it was a very significant one, which is no surprise. However, there are only 2 studies that have recently definitively tended to show this, and efforts to duplicate those results by DTU were not successful. And so if you read all of the papers that have been published in the last 3 or 4 years, you'll find that the efforts by Prof. and his group at DTU to replicate the studies that were done by Satish have generally been failures. And they did one interesting thing that wasn't done in the other study, which was they not only looked at injecting pure CO2, they also changed the CO2 concentration by changing the ventilation rate. So they had data where the bioeffluent concentration changed along with the ventilation, with the CO2 concentration, and where it didn't. And they found 2 things. One was that the concentrations of CO2 at which there were noticeable cognitive function deficits was much higher than in the Satish et al. Studies, and that only happened when the bioeffluent concentration changed too, which gives the kind of depressing academic result that we did a study and found out that the way we believed things were in the past is probably still true. But the jury is still somewhat out on this. So that's the story I have on the nature of our current IEQ standards, and I think it's a situation that could be much better than it is. So now we move to the issue of energy consumption as affected by ventilation, particularly, which is our main way of controlling exposures. And I would make the blanket statement that you could argue with that energy and efficiency and IEQ tend to be at odds with one another in the minds of designers, and that energy usually wins. So why is that? Energy is measured accurately, it's monetized. We know that efficiency has a positive environmental impact. We reduce greenhouse gas emissions, and we have an existing design process that everyone's familiar with, where we optimize the construction cost and the operating cost of the building. On the indoor air quality side, we have prescriptive standards that do not really quantify the effects in the same way that energy standards do. So we are either on the right side or the wrong side of the ventilation rate criterion. Going along with that, we don't have very accurate monetization yet of IEQ or other aspects of IEQ. And it's certainly true that if we're not careful about how we do things like increase ventilation rates, we are likely to have energy penalties which detract from the overall benefit of what we're doing. And finally, we have ventilation standing in for air quality as a design constraint rather than as something that we optimize. So that's where we are. What do we need to do? Well, an agenda for better integrating IEQ and energy efficiency, in my view, would include these things. First, a lot more translational research from science to application. Indoor air quality is a diverse field that has researchers who may have qualifications as medical doctors, as industrial hygienists, as chemists, as microbiologists, who don't really know much of anything about buildings. And so we've been piling up research that's very interesting that hasn't really had yet a highly significant impact on our standards or our design practices. So that's something that the academic and research community can do. We need education and training for building designers and building operators that makes them better able to make judgments about whether their buildings are going to perform well in the case of design or are performing well in the case of operation. Then we need to have better ways to create better IEQ, to deploy efficient technology to improve it, which is what we'll focus on here in the remainder of the presentation. And we need some design process changes, which I'll touch on briefly as well. When we look at solutions, I should reiterate here that engineering controls, what we do as HVAC designers, if that's what we do, are not the first place to start. Elimination of sources has always been the best way to improve indoor air quality. Substituting where we can't completely eliminate to reduce emissions is another way. And then the third level is engineering controls. And we'll focus on those. And we'll focus actually mainly on ventilation, a little bit on other things. Ventilation is important because it's what is generally done in buildings to control indoor air quality. And I came up with a list of 6 things that we could do to try to make ventilation more efficient. The first of them being to use natural ventilation in more buildings. So if you go to the developing world, Asia in particular, there's a very big focus on natural ventilation because they don't have the means to build buildings that are air conditioned, cooled the way that we do them in the US and perhaps in Western Europe and other highly developed parts of the world. In a country like the US, it's been estimated that we could, if we tried, meet 20 to 50% of our cooling needs from natural ventilation. But there are a lot of caveats that go along with that. In urban environments, increasingly we're seeing higher ambient levels of pollution. That's not so much the case in the US, but if you go to major cities in Indian subcontinent, Asia, New Delhi, Beijing, others, we know that they have very serious outdoor air problems that make that air not so suitable for ventilation. Also, there are concerns about the seasonal effectiveness and the occupant impact of natural ventilation. If we're going to apply natural ventilation in a more widespread way, we're going to have to buy in to the notion of adaptive thermal comfort, replacing the older predicted mean load percentage of people dissatisfied approach that we've used for a long time. And built into that is the notion that the occupants of a building will adapt if conditions are not their liking. So if it's hot, they will first perhaps change their dress, and if they change their dress to the extent that they can, and they're still not comfortable, then they may just not work as hard or work less. We have the tradition of the siesta in the middle of the day in hot climates where there wasn't air conditioning. So these sorts of things will have an economic effect if we do them. And we also have the problem that in some standards you have to have backup systems for natural ventilation if you can't do it all the time. But it's something to consider where it is applicable. Heat recovery for air is another very good solution, and we've made a lot of progress over the past few decades in better air energy recovery devices. Total energy recovery, where we can transfer both latent and sensible heat, is perhaps the biggest improvement that we have. And we find in standards now that there are requirements for total energy recovery in, for example, ASHRAE Standard 90.1, which take a sort of a broad band of outdoor air conditions and squeezes them down into a range that results in lower loads on our coils, whether that's in the summer and we're conditioning outdoor air to cool, or in the winter and we're bringing in outdoor air and we're going to have to heat it. Another thing that we can do to reduce the cost of ventilation is demand-controlled ventilation or dynamic ventilation, where we try to limit the amount of ventilation based on something like the number of occupants. We can also do it based on things like indoor particulate matter concentration, VOCs, or even humidity, but the sense in which it's typically used with respect to ventilation is trying to only provide as much outdoor air for ventilation as we need for the number of occupants in the building at that point in time. And again, we find that in energy standards, people who write those have picked up on that. They may not know a lot about the effect of doing that on the occupants. I am lukewarm about this as an approach for a number of reasons. One is that getting an accurate occupancy count is not so easy, especially when you try to do it with CO2 sensors, which is the way that this is most commonly done. The second is that I've already tried to make the case that our minimum standards are too low. So if we now enforce the minimum standard 100% of the time instead of allowing the building to be over-ventilated some of the time, we're probably going to make the indoor air quality worse, even though we think we're just meeting our standard. So the case in which I would support this sort of an approach would be if we could increase those per-person ventilation rates and then use demand-controlled ventilation. There have been some interesting studies done on that in recent times. The earliest one that I saw was this doctoral dissertation from, I think it was Lund University by Johansson, and he took the dose response relationships that he could find for various indoor pollutants and included those energy cost and construction cost of systems and the salary paid to workers, and tried to come up with life cycle cost optimized ventilation rates. And a figure from his energy and building and environment paper is shown here, where we have salary on one axis and the optimal ventilation rate on the other. And the green curve is constant volume ventilation, and the orange one is variable volume, and you can see that at any given salary, the amount of ventilation here that can be provided that's cost optimal is higher. Another approach that works is to use air side economizers where that's feasible. Again, this is somewhat of a regional approach. In the US, we have lots and lots of variable air volume systems that are all air, and they're required by energy codes to have air side economizers. If you're not familiar with that approach, we compare the outside air temperature or enthalpy to the return air temperature or enthalpy, and when conditions are favorable, we bring in more outside air to reduce the load on the cooling coil. So we do that to save energy. But coincidentally, we're also raising the average ventilation rate in a building, but no one ever really talks about that. I've seen one paper in my entire career that deals with that, and it was done by Fisk and Seppin and some others, where they looked at an office building in Washington, D.C. and modeled it with and without an air side economizer, and then used the Wells-Riley equation that I mentioned before to try to estimate the effect of the difference in average ventilation rates on simply the occupants. And so what they found is shown in the summary table. They looked at 10, 15, and 20 liters per second per person as the base ventilation rates. And what you see in this climate, just for 10 liters per second, is when you go from no economizer to an economizer, it doubled the average annual ventilation air change rate, which has a fairly significant effect when you run that through the Wells-Riley equation. So then they calculated the energy savings, 1,900 USD per year, and when they used their estimates of the difference in sick leave that would result and monetized that, they came up with $13,000 to $16,000 per year. So overall in this study, they showed a 3 to 8 times greater health benefit than energy benefit in that study. Another approach we can use is dual path or dedicated outdoor air systems. There's a whole ASHRAE design guide on this that was published recently. Here the significant thing for air quality is that we have a 100% outside air handling unit that delivers ventilation air as required to all the spaces at all times. So we don't have problems with reduction in outside air from VAV operation or the problems of mixing. And then we meet the terminal sensible loads with some kind of parallel system like a fan coil or a chilled beam or a radiant panel, or even a parallel recirculating air system if we want to be able to do outside air economizer. So we get positive ventilation, and we have air handling units that incorporate the best kind of energy recovery that we can put into them. There are many different configurations for these air handling units, but here's one with a total energy wheel that exchanges enthalpy first between the incoming outside air and the exhaust air. So if this is summer, this is hot and humid, and we take indoor air and we use that to reduce the temperature and the humidity before it goes to the cooling coil, which does the rest of the refrigerant dehumidification, which sometimes results in having air that is so cold that it overcools a space. So the parallel plate sensible device here is to give some free reheat before you go to the terminal reheat coil if that's necessary. But this is an approach that would work if you had a climate in which you were overcooling a lot of the time. There are many other ways to skin that cat. Stan Muma, my colleague at Penn State, who did a lot of work on this 10 or 15 years ago, installed the system in one of our classrooms, And the study here that's excerpted shows a comparison between the predicted energy use of that DOAS system and a VAV system. That's what we had in that environment. And the difference in energy use annually was predicted to be about a factor of 2 difference. Yet another thing we can do to make ventilation more efficient is to deliver the outside air to the breathing zone to remove contaminants more efficiently. And so things like underfloor, or in this case, displacement ventilation can work significantly better than overhead mixing ventilation that we have in the majority of our buildings. So that allows you to reduce the amount of ventilation for a given level of air quality. And then we can try to limit our need for ventilation by using air cleaners to remove contaminants that ventilation won't remove, and to help us not have to condition so much outside air. So we have particulates, gas phase contaminants, and microbial contaminants. We use filters both for PM, as was discussed before, the kinds of stuff that causes those health effects, and also to remove microorganisms. We have well-developed, well-understood technology that produces filters that have characteristics as shown over here on the right-hand side. These are MERV-rated filter curves. MERV 8 is about where we are right now with standard 62.1, and you see down here the 1 micron or so particle size range. We're looking at less than 10% efficiency. What we really need to get to is probably more up at around 12 or 13. We don't need to go to HEPA, which is very expensive. Interesting study that was done at University of British Columbia looked at what would happen if we put MERV filters of varying ratings, higher is better, in the outside air path in different locations. So from Vancouver, that's very clean, up to Delhi, which was probably the worst at the time. And what we're seeing here is US dollars per year in health benefit, morbidity and mortality, netted, including energy and equipment, as the MERV rating changes. And so you see here, the worse the outside air is, the bigger the benefit is. And we also see that as the MERV rating goes up, things get better. There's a big change at 11. This is an example for London that shows that most of the benefit is in reduced mortality, a little bit morbidity, and the added costs are relatively small. Why this big jump here? It's because when you get up to 11 or 12 MERV filter, you're finally starting to get a significant amount of PM 2.5 out of the air. Gas phase air cleaners are not yet in widespread use for a number of reasons. They're not required in prescriptive standards, partly because sorbents, the main media we use, are expensive, and they may not actually work as well as we would like them to. Photocatalysis is something that has promise. It was mentioned in the talk on materials. There's a good poster on photocatalysis out in the poster session as well. This is something that's coming, but not yet very well applied in buildings, only in special environments. For microbial contaminants, as I mentioned, we can use particulate filtration, but the smaller the particle, the more expensive that tends to be. An alternative to that that's quite effective is ultraviolet germicidal irradiation. Low pressure drop, low energy use, and known to work well. There are other methods as well, but we don't have time to go into a lot of details here today. What UVGI does is disrupt the DNA or RNA of microorganisms so they can't replicate. That's a well-studied phenomenon, and this is the germicidal effectiveness curve. It's a function of wavelength that maxes out at about 265. We can make a lot of 254 nanometer UVC with low pressure mercury vapor lamps, and LEDs are coming that will maybe get us to that peak cost effectively in the future. How does UVGI work? Strength of the radiation, the time of exposure, and the microbial susceptibility are what determine how well it works, and we can design systems that way. Typical applications are to put UV in the duct of an HVAC system, particularly in the air handling unit, so we can irradiate the coil as well as the air. Or we put it in occupied spaces to create an irradiated cavity above the occupied zone. Coil UVGI is something that we've studied at Penn State a lot in recent times, and this is a way to do some air treatment and also get an energy benefit on the air distribution side. So we studied some installations in the US and Singapore, and these are some of our results. We see pressure drop improvement when we irradiate the coil and get the microbial slime off of it. The red are the before UV data from a system in Singapore. The blue are after, and you can see the two trend lines here. Result of that was an improvement of roughly 10 to 15% in air side heat transfer coefficient, and that results in lower chilled water flow rate due to a larger delta T. And over here we have some simulated savings based on the reduction in air side pressure drop and increase of the transfer coefficient that we found. Another thing to mention here, and this is maybe a controversial point, but I like making it, is that the more renewable energy we have, maybe the less we'll worry about some of the consequences of using a little more energy. Not a lot. There's always a good reason to save energy, but one of the reasons we don't want to use it now is because it's producing environmental pollution. So perhaps it will change the economics of this a little bit. And so now the final point here, that was the technology piece. How would processes change if we were integrating IAQ and energy the way we'd like to? Over here on the right-hand side, I think my battery is dead, which is another way of telling me I'm just about out of time. The process that we typically use now to optimize the performance of a building. We start out with a scenario that looks at the construction cost, the energy and water cost, and the maintenance cost. We get that by running an energy simulation, and then we optimize those things, and we only stick IAQ in as ventilation rate that affects our energy use. What we need to do is put some additional pieces into this process where we do an exposure model and a dose response model and monetize that so that that difference in cost for different system designs also goes into that optimization. If we could do that, it would change the outcomes that we would say were the best in just about every case. So to conclude, while energy use of buildings is a very important problem that we need to keep working on, indoor air quality and its consequences may be an even bigger problem in some ways, and we need to do something about that, but recognizing that it has potentially a negative impact on energy use. The consequences of the data that I've seen in the literature, the things that I showed you and others, is that we really ought to think about changing our minimum standards, and maybe you'll hear something about the direction that's going from the next talk. And then the final point is that, and this is almost always true when we think something needs to change, is that we don't need to wait for a new generation of technology to do a lot better than we're doing right now in terms of the energy use of buildings as affected by the indoor air quality delivered. We've got lots of ways that we can do that if we want to include them in our designs right now. And so that's my message, but I'll end with a gift to everyone. If you haven't downloaded this from the ASHRAE website yet and looked at it, there's an ASHRAE IAQ guide that covers construction through commissioning, and you can get that free from the ASHRAE website. It has a lot of very good information on the different aspects of air quality and how they can be controlled using existing technology, and how processes of construction and of commissioning can help us do that better as well. And with that, I will conclude, and if there's time, I'll be happy to have questions and comments. Thank you.